Hello everyone. Today in this lecture we will continue integrated optical components. In the last lecture we have discussed about Y junction power splitter, combiner and also Mach Zehnder interferometer based on Y junction and also the transfer matrix of the Mach Zehnder interferometer. So, now we will discuss directional coupler. Sometimes directional coupler also used as a 3 dB power splitter to construct 2 by 2 Mach Zehnder interferometer, and many other components also like ring resonator etc. Design directional coupler play a major role. So, basically directional coupler is nothing but coupled waveguides. Two waveguides, they can be parallel, they can be unparalleled, they can have different type of configuration. As long as they are coupled somehow, they can transfer energy between them, then that will be called, they will be called as a coupled waveguides. And in the coupled waveguides, if you have a suitable design control, then you can use them as a directional coupler. And in this lecture, we will be first discussing about conceptual working principle that will help us to understand, visualize how a directional coupler works. Little bit mathematical model we will be considering, especially super mode theory, super mode principle we will be using, but we will finally we will see that that type of conceptual understanding is not enough to quantify particularly amplitude and phase when light coupled from one waveguide to another waveguide. So, for that actually we have to solve really coupled differential equations. We have already discussed earlier coupled differential equation between modes, but those modes are within one waveguide. That those modes can be propagating in the forward direction, can be propagating in the counter propagating direction, but they should belong to the same waveguide. But here we want to construct a coupled differential equation between waveguides, waveguide modes, two different waveguide modes, one mode from one waveguide, another mode from another waveguide, and how they are coupled. That type of differential equation we have to develop to understand directional coupler and quantify the amplitude splitting and phase relationship between the splitting amplitudes, splitting waves. So, that is very important, little bit differently, but almost same way we will be constructing this coupled mode coupled differential equations. That is what we will learn today. So, let us take example of this figure. Okay. Let us try to understand step by step. You have this is the box. I have not shown the substrate. Below there will be a substrate, silicon substrate, and silicon on insulator. This is the device layer H, which is fixed about 220 nanometer nowadays. It can be anything but fixed. And we have, this is your H, and this one is your waveguide width, and this is totally, when you say H, then little bit of slab you are keeping, small h, and that small h also maintained in between two waveguides, and they are separated by a distance S naught, separation S naught we are just considering. And as you know, we can just define this box refractive index, silicon dioxide refractive index, and cladding here can be oxide, can be nitride, and then ND, that means device layer refractive index, that means silicon refractive index, right. And we can just think of that whenever you are just solving this mode, thinking that this is not present, this waveguide, this can be considered as a waveguide A, and this can be considered as a waveguide B, A and B. When you solve electric field distributions using standard full vectorial methods, and you can consider EA is the dominant electric field components, you can use them as a scalar, say T like or Tm like when dominant either along x direction or y direction. That field if you concentrate, that field distribution if you solve, that is the mode we define like this, and we can assume that this waveguide is designed such that it only support fundamental mode. Similarly, another waveguide, the W small h capital H, you design such that it also gives you fundamental mode. It is a single mode supporting, it is not a multi-mode waveguides. Individually they are multi-mode waveguides. If you solve individually thinking that when you are solving for A, you are thinking that B was not there, and when you are solving for A, then B, then you are thinking waveguide A was not there. So, if you solve like that, that is the field distribution. Corresponding field distribution is this one, corresponding field distribution for waveguide B is this one, EB, EA. They will be, if they are identical waveguide, they will be identical field distribution, only their field distribution will be laterally shifted, that is it, depending on the S naught. So, whatever field distribution you are getting here, you just shift S naught distance, whatever the center to center distance, if you just change, then you should be getting the field distribution like that if they are identical, and corresponding propagation constant beta A and beta B you will be getting. If they are identical, beta B equal to say your beta naught omega by C n effective naught, and beta A also should be equal to beta naught omega by C n effective naught. So, if we are considering identical uncoupled single mode waveguides, so they are uncoupled, they are far away, or you are just considering they are not interacting at all, or you are considering they are just simply decoupled. Top view you can see here. This is the top view, and the field distribution, I am just considering this S is selected much higher than S naught, where S naught may be the actually desired waveguide separation you want for that, so that they can be coupled, they can interact. So, whenever you are putting a separation far away, as if they are individual identity, there is no coupling, no interaction between them, then we can consider okay, one field, top view I can show EA XY, only X distribution shown here, Y direction it is same, we are considering Y direction, the field mode will not be changed. So, it will be like a whatever shape you will be getting in the cross section, just I am just getting in the XZ projection, X direction, what is the electric field strength, in the central it will be maxima, and slowly it will be decaying, evanescent tail will be there for waveguide A, similarly for waveguide B. So, if they are identical, again you can see that their shape will be identical, but they will be positioned at different x coordinate. Y direction their field distribution will be similar, okay, vertical direction. So, following the orthonormality condition, you know that orthogonality condition we write that E A star x y, E A x y, dx dy, they are actually modes from the same field, and that will be actually we will be writing 2 omega mu by beta A, because only one mode is there. So, I can say that this is nothing but this thing dx dy, and if you are defining that this field has an amplitude, specific amplitude, normalization constant, and then propagation constant beta A should be beta naught, beta A equal to beta naught if they are identical, and for waveguide B, so E B x y omega t minus beta b j naught, beta b z, and so on, and you have the constant normalization constant such that A square equal to B square equal to 1 watt, individually they are carrying 1 watt. That is what we keep on considering all the time. Okay. So, again you should not forget that this EAXY, whatever we are writing EBXY, they are in principle their distribution profile is same, but coordinate wise when we just consider relative position of two waveguide, they are at different position, that is it. Okay. And since they are not coupled, this field when it is propagated, that will be propagated here, and if it is launched 1 watt, you will be getting 1 watt. If it is lossless, 1 watt if you are launching here, 1 watt lossless, again you will be launching maybe 1 watt here, 1 watt, this is just a reference, it can be 1 milliwatt, 1 watt it will be coming. There is no interaction, they will be propagating. If it is lossless, suppose you can imagine if there is a 3 dB loss because of the scattering etc., then you will be getting here 0.5 watt, and this is also 3 dB, it will be 0.5 5 watt. Some losses there, that means it will be half, that is it. Otherwise, they are independently propagating. Yeah. So far so good, and we are considering that whatever frequency we are launching here, the same frequency here, that is fine, and whatever phase will be there, initial phase e to the power j delta, that in travelling distance e to the power, you will be getting beta a l, l distance travelling, and then initial delta you will be phase change you will be considering, same will be here. So, it is as good as like a individual waveguides, two identical waveguides separated at a distance when they are not at all interacting. When we will call them not at all interacting? When the evanescent tail, you know, this evanescent tail will be decaying and it will be 0 only at x equal to infinity or this around infinity, and here also evanescent tail it will be decaying, but at infinity it will be 0. But if you see after a depth skin, so called skin depth or something like that, the evanescent tail will be decaying very fast and nearly 0 you will be getting here. So, as long as they are nearly 0, that means it will not see, this mode will not see the presence of the second waveguide and vice versa. But when you see that the separation reduced to S naught, that is our desired one, when you see that evanescent tail of the waveguide A is penetrating through the separation gap and entering into the, it sees some presence of the evanescent tail, sees the presence of the second waveguide and vice versa. A mode, this one, it sees the presence of the waveguide A. The mode in waveguide B sees the presence of waveguide A experiencing the presence. So, when evanescent tail sees there, this evanescent tail here supposed to see not waveguide, maybe if it is some slab is there, it is supposed to see slab. Instead of slab, the evanescent tail it is going like this and it is coming like this. Okay. So, if this waveguide was not there, this waveguide was not there, the field would not see this refractive index, the additional height, presence of second waveguide. So, that means this waveguide presence, what it will see, some type of kind of perturbation, this waveguide will see some kind of perturbation. So, that is how we can consider this perturbation theory or coupling, some way of coupling it you will see. Okay. So, in that situation we cannot really consider something like this type of mode and this type of mode individually, because they themselves is no more following orthogonality condition, orthonormality condition, rather they are interacting each other. So, orthogonality condition is broken and instead of this, these two mode will lose their identity. Rather, what you will see? You will see two super modes, we call them as a super modes. How these super modes are constructed? One is called symmetric super mode, that is the waveguide field distribution for waveguide A, field distribution for waveguide B, linear combination. That is simple superposition. And if you do this adding the field amplitudes here, for example, you will be getting this type of shape, that is called symmetric super mode. Symmetric super mode. But you can also imagine another type of superposition, that is subtracting. That means you see EA, EB, they are different position, but you know they will be oscillating all the time, oscillating back and forth depending on the time according to the frequency of the electromagnetic wave. So, what you could see that their linear combination plus and minus, they will be jointly giving another type of super modes, and that will be called as asymmetric. This type of concept normally used in solid state physics also and molecular science, where actually two wave function of electron, if one atom wave function is this one, another atom wave function is this one, electronic wave function. If they are coming close by, then electron from one atom and electron from another atom, their state they will be interacting each other. Okay. So, when they will be interacting each other, the energy, even though suppose two hydrogen atom you are considering, they are brought together closer, then one s electron and one s electron here, they will overlap. After overlapping, their energy level will be split it and it will create two different wave function. So, that is called actually in solid state physics or molecular spectroscopy, you call it as a linear combination of atomic orbital, linear combination of atomic orbital. You can imagine also here one photon state wave function is like that, another photon function wave function is like that, and these two when it is coming closer they will be actually interacting each other, and that will give you some kind of splitting of the two different wave function. In case of it, sometimes you know electronic states in a crystal, it is normally splitted because of the presence of some kind of perturbation. Here also this perturbation actually causing some kind of splitting, we call them as supermodes. And when they are splitted, what you would see, their propagation constant, that is the eigenvalue, right. Field distribution you get as a solution, you get a eigenvector, and beta solution you get a eigenvalue, right. So, originally individually when they are separated you are getting beta naught, here also solution was beta naught, but as they are interacting each other you will be getting two different solution. One will be delta beta added, this propagation constant, another minus, exactly it will be reduced. So, some value will be added here. So, you will be getting one higher propagation constant, another will be lower propagation constant. It is like that if one energy is there because of the field or maybe magnetic field, you know G-man effect, etc., or if some magnetic field is there, some energy level split it like this. So, this type of energy will be splitted. This one will be beta naught and this will be beta s and this will be beta as. Beta is equal to beta naught plus delta beta and this will be beta naught minus delta beta. So, that way it will be splitting. We just qualitatively here we can assume that these two modes they can linearly, they can have some kind of linear combination of modes. You can get symmetric mode, you can get asymmetric mode, and you can have two different propagation constant, so called beta s, beta as. Obviously, beta s greater than beta as normally you will be getting. Okay. So, they are called supermodes, and these supermodes can be again normalized with a constant, normalization constant as for asymmetric, and for symmetric it is a as and this is as, this as subscript is there. And then electric field also profile, symmetric and asymmetric you can just define. Symmetric means this one coming profile, just spatially you are just adding at a distance, but here spatially we are adding, but one will be opposite phase. That is actually two types of superposition you can expect. Two wave function, it is giving two supermodes. If it is 3, then you would expect 3 or more different combination of linear combination you would be observing, fine. And accordingly you can normalize this one, this normalization like a standard. You can consider these two as a eigenmode of the combined system. Okay. Even if you solve full vectorial methods, complete this structure, then you would be getting two more solutions. One will fundamental mode will be looking like that and next higher order mode will be looking like that. So, you can consider they are as if they are eigenmodes, and those eigenmodes, this will be the first order eigenmodes, so called symmetric supermode, and that will be asymmetric supermodes. So, this type of solutions you can expect. Good. So, now you just take this cartoon, help of this cartoon. Suppose you consider that you are launching, suppose in the beginning, suppose this waveguide starts from here, second waveguide B. You are just launching here some mode in the first waveguide A you are launching, and you are launching suppose 1 watt power, A square equal to 1 watt, right. So, this is the when that is not coupled, A square equal to 1 watt. So, A equal to 1 you are just launching. At Z equal to 0, just when it is starting, two modes to couple. Suppose it is extended here and you are launching like this and it has started coupling here, this is actually Z equal to 0. This Z equal to 0, what happens? You know the combined waveguide has two solutions. So, it is like that whenever you are considering a Y junction like this, Y junction waveguide, you have fundamental mode is coming and you have two paths here. So, if it is lossless adiabatic one, if the amplitude A it is coming here, then it will be A by root 2, it will be A by root 2 because of the two paths. So, similarly, you can think of that whenever a mode is coupled with a amplitude say 1 or 1 watt power, amplitude 1 we can consider 1 watt square, that is A square is equal to 1 watt, that means A equal to 1. So, in that case what you have also two options, it is like a Y junction, you have two paths, but here it is a coupled waveguide, but you have two options. So, in this two options, if you see the symmetric mode and asymmetric mode, if you see that overlap here, this part integration of this one, you will get some value excitation here, and this one with this one, if you just see the overlap, also you can get some kind of value. So, it will be also coupled, but in that case you will be getting asymmetric and symmetric mode propagation, but amplitude will be now A by root 2, 1 by root 2 here and 1 by root 2 here. That is what it is given. AS will be 1 by root 2 and this will be 1 by root 2. That means AS square will be 1 by 2, AS square equal to 1 by 2. So, if it is A equal to 1 watt, this will be 0.5 watt, this will be 0.5 watt, that is what we mentioned. So, that means if I launch 1 watt with in one of the waveguide in fundamental mode, when they are coupling to each other, then this power will be instantly at z equal to 0. It is like a Y junction, it will be divided into two amplitudes, one will be 1 by root 2, another will be 1 by root 2. So, 50% power will be associated with this mode and 50% power will be associated with this mode. Once they are excited, they will be traveling with different phase velocity, because their propagation constants are different, they will be traveling with different phase velocity. Okay? So, that is the idea. Now, let us consider this one. If you are just instead of this one, you are launching here in the second waveguide you are giving, and you are giving 1 watt. So, that this B amplitude is 1, A equal to 0 for example. I am not giving anything in waveguide A. So, in that case also at z equal to 0, you see you will be getting 50% excitation to 50% power will go to symmetric mode, because these are the solutions available, these are the path available in the waveguide. Any electromagnetic wave, if you are launching in this system and if they are interacting, you have two options are there, excitations. No other excitation is there, even if it is there, you are ignoring that, you are just considering that okay, there is no other possibility is there, light cannot tunnel to any other radiating mode. So, in that case, here also you will be seeing that it is excited super mode, symmetric super mode will be excited this one, and this will be excited like this one. Field distribution, amplitude, it is either you are launching here or launching here, you will see similar type of situations. So, it will be two super modes will be excited. Now interesting, suppose you are launching first waveguide also 1 watt, second waveguide also you are launching 1 watt. Both waveguides you are giving amplitude like that. What happens? It is interesting. In the first waveguide you will see this is corresponding to waveguide A, this is corresponding to waveguide A. So, from waveguide A you will be getting these super modes and this is this super mode, symmetric super mode, anti-symmetric super mode, and from waveguide B you will be getting also another super modes, symmetric, another super mode symmetric. So, that means if you see, I know that this mode will give one super modes here, symmetric and anti-symmetric, this one also will be symmetric, anti-symmetric. So, there will be 4 super modes now, because 2 modes we have excited here. So, I would expect 4 super modes, and out of these 4 super modes, these 2 supposed to be same, right, they are degenerate, their propagation constant will be same, because their solutions are different, but you see 2 solutions are there, one coming from waveguide A, another coming from waveguide B, okay, launching waveguide B. So, 2 types of, meaning they are actually ultimately same, but since propagation constant is same, but you can treat them individually, they can be considered as degenerate, but that is actually one mode solutions you can think of. Similarly, here also degenerate asymmetric supermodes are there. Let me refresh. So, this is A coming from A and this is also coming from E. This is B and this is coming from B. Okay. So, if you see this one A and A, if you superimpose this side positive, this will give you this one, and this was positive, this side negative, that means waveguide A excitation will actually result into this one. Add this 2, you will be getting this thing. Add this 2, you will be getting this thing. So, that is how it is decomposed into 2 degenerate supermodes, symmetric supermodes, 2 degenerate asymmetric supermodes. Okay. That type of situation can happen. Fine. Now, I come back to again this situation that where you are launching only in the waveguide A. Waveguide A you are launching here. And you have this one 1 by root 2 and this one 1 by root 2. And they will be travelling with beta S and beta AS. Suppose you know what is their propagation constant. Okay. And this type of situation at z equal to 0 you can see. Whatever I am, though I am just sketching at arbitrary z point, but this type of excitation happens exactly at z equal to 0. Okay. So, half what you can excite to symmetric supermodes and antisymmetric supermode, and you allow them to propagate. Here from z equal to 0 to, you just think about some z equal to LC. I am now looking into the supermodes at certain length where the supermodes, this one, their phase difference, this one and this one, if you see previous one to this one. Now, what I see at z equal to 0, I see this one, right, because if you just add this one, you are just reproducing this one, this negative plus, that should be cancelled. And now, if after travelling a z equal to LC, I am just considering at LC what is happening. This one will be in phase, after travelling it will acquire some phase, right. So, for example, beta S LC, it is something 2 m pi, phase shift is there, first symmetric supermode, and antisymmetric supermodes you are getting something like that, beta S LC you are getting 2 m pi plus pi, additional phase shift is there. So, when it is additional phase shift is there, that means if you just compare this one, so this one and then this one, this only this much flipped. So, once if it is flipped after propagating LC distance, that means asymmetric supermodes is pi phase ahead of symmetric supermode. So, in that case, if you just add them together, this minus and this plus, they will cancel each other, this plus, this plus. So, your energy, major energy will be here, plus is there, so here. So, at this LC distance, exactly at LC, if you start decoupling your waveguide here, for example, two waveguide decoupled, then what happens? This waveguide will not carry any energy, whatever mode is there, you will get better overlap here, it will be coupled to the waveguide B. You are launching here in waveguide A, but light will be coupled to the waveguide B after travelling LC. LC is the distance where phase difference you are getting beta S minus beta S LC, beta S LC 2 m pi and beta AS LC 2 m pi plus pi. So, if you subtract, so then you will be getting this one. Normally, this one will be minus pi, it will be, because this will be lower, beta AS is lower. So, 2 m pi minus pi, that is why you will be getting pi. So, if you allow to travel them, after travelling a certain distance, if they acquire, initially their phase was same, it is 0 phase with respect to here, whatever excitation is there at that time, we are considering their phase difference is 0. Now, as they propagate, and we said that whatever phase relationship is there probably, and then after certain LC distance travelling, you see pi phase shift. In that case, superposition if you see, you will be getting like this. Okay. Now see, if I instead of pi phase shift, if you allow distance such that you get their phase difference is e to the power j pi by 2, not pi, pi by 2. So, pi by 2 means what is the difference? Beta s minus beta s, L 3 dB by 2 instead of pi, pi by 2. That means just half the length. Whatever LC was there, when light was launched here, you are exactly everything you are getting here. You just go just half distance. If LC distance it provides pi phase shift, half of the travel length it will give pi by 2 phase shift. So, in that case you cannot really define very nicely like this side positive and negative clearly. You have to add, you have to have a factor like this e to the power j pi by 2. So, in that case after adding this phase and if you do some superposition and then this superposition will see field strength like this. It will be 50% field strength here and 50% field strength here. And at this point if you just separate, decouple, then this fraction will lead to this waveguide, this fraction will lead to this waveguide. Suddenly you are breaking the orthogonality condition here. Orthogonality condition for supermodes, asymmetric supermodes starts here at z equal to 0. As long as you maintain the coupled waveguide cross section, then they will travel like a orthogonal modes. Now, once you see field strength is reasonably good shape in first waveguide, total field strength and second waveguide, there then and there you just do separating them. Then you get exactly 50% power here in the waveguide A, 50% power here, and in that case we will be calling that as a 3 dB power splitter. It is exactly equivalent to Y junction power splitter, right. In Y junction you have one waveguide and you have two branches, right. So, you just get like this, get like this. So, in this case 50% goes here, 50% comes here. Here also you see, if you just maintain, if you know beta s and beta as, you just define a length, find a length, you can find out what is the L3 dB here. L3 dB equal to actually pi by 2 times beta s minus beta s minus beta as. So, if you can solve this propagation constant for symmetric supermodes and asymmetric supermodes, you know what is the length required to get a 3 dB power splitting. What is the length required to be a complete power switching from one waveguide to another waveguide or vice versa. So, that type of LC will be exactly LC, then it is like pi by beta s minus beta as. Okay. Beta as can be also, you can define beta as equal to omega by c or 2 pi c by lambda into n effective s, and beta as will be omega by c n effective as. So, if you do mode solving of this entire structure, then you can get two supermode solutions you will be getting also from full vectorial method. If you do, then you can get symmetric supermode will have a n effective s and asymmetric supermode n effective as. Once you know that, then you can find out this one, and omega by c if you put lambda by 2, lambda by so on, then you can get also very nicely. Once you know the effective index profile indices of the symmetric and asymmetric mode, then you can calculate what is the length required for full coupling, what is the length required for 3 dB coupling, and then you can scale the length and you try to find out actually what is the length required to split power with a desired amount or a desired splitting ratio you can find out. Okay, good. So, we know that if two waveguides are there, if they are interacting each other, even if a tail is reaching to other waveguide, then they starts interacting and power can couple through a supermode excitations. Whenever, as long as you are maintaining that type of coupled parallelism, parallel waveguides, then the supermodes are eigenmodes, they will be carrying energy individually, independently, but when you see their superposition effect is suitable to have certain percentage of power in a second waveguide, you terminate there, break the orthogonality condition, then you get a desired splitting ratio. Okay. This is actually somehow we can conceptually, some mathematical help we took, mathematical model, supermode excitation, etc., but we understand that you can really indeed you can design a complete power coupling directional coupler or 3 dB power splitter or maybe 6 dB power splitters. That means 6 dB will be that means 25% will be coupled to the second waveguide, 75% will remain in the first waveguide, that so on. You can do that, you can design directional coupler. Now, you have certain problem to design. If you want to use this type of directional coupler to design a complex circuit like Mach Zehnder or maybe ring resonator or maybe cascaded Mach Zehnder interferometer or more complex circuits we will learn in course of time. In that case, we would like to understand little more, just not the power splitting ratio is enough. You need to learn little more. What are those things? Let us consider, will there be any phase difference between the output field when decoupled? So, when you are just decoupling here, suppose 3 dB power splitter LDC is there, some power is here, some power is here. Now, question is that I just decoupled here, they are originated from the same source. Now, when you are separated them, what would be their phase difference? That is the interesting point. Normally, in Y junction, what you see? Y junction, you see your mode is coming like that and it is identical situation here, identical situation here with respect to this mode. That is why whatever phase it will be acquired in the junction, the same phase will be acquired in the second waveguide. But in this case, if you see, some power is retained in the first waveguide and some power actually tunneled to the second waveguide. So, when it is tunneled to the second waveguide, do you expect their phase will be same? It may be different, but that thing we will not be able to learn from the super mode, that working principle, whatever the conceptual discussion we did so far. That gives us actually pretty good understanding that really coupled waveguide, if it is there, you can really couple light, you can tunnel light according to your things. But if you want to use them for not for just splitter, you want to use them for in a photonic integrated circuits. In that case, normally you have to interface another device. Whenever interfacing one device to another device, you do not work with the power intensity, rather you work with the amplitude and phase. Because integrated photonic circuits, entire circuits you can analyze in terms of amplitude, because there is a phase relationship that can cause some kind of interference. Okay. So, that is one first question, that we will not be, we need to know not only the power, because whenever you are just measuring power, you are losing the phase information basically, because whatever photodetector if you are just using also, just measuring power, you cannot recover the phase. Now, how to design a DC length to obtain any desired output power splitting ratio? So, suppose I just consider, okay, 3 dB I need this much and I need 50%, 25%, I can just cut linearly, I can cut. Is that the right thing, that if you just do half and half, if you just make a, if this is LC complete coupling there, you just make a half 50% and another half, then it will be 25%, another half, then it will be 12.5%. That way it works. Really, is that linear? That power will be linear according to the phase difference, because normal total phase difference it will be beta S minus beta AS L, that is the total phase difference, if this is suppose delta beta. Now, according to this thing, it is true that phase can be half delta beta, that is delta beta L, right, that is the delta phi, sorry, this should be delta phi. So, if a L instead of L by 2, then phi will be delta phi by 2. So, you can actually phase linearly, as a function of length, phase is linear, but output power also will be linear. It is not proportional to phase difference, this power in the output is not at all proportional to the phase. Phase is proportional to length, that is true, beta S minus beta AS L, that is actually phase difference between symmetric and asymmetric, that is true, but this phase actually not contributing a linear power splitting ratio in the two output waveguides. The power splitting ratio is not proportional to delta phi, it is not. So, that information we will not be getting. here. What else? How to model the DC if the coupled waveguides are not identical. So far we have been discussing this is a beta A and this is beta B, and then if it is identical, then 3 dB splitting, 3 dB splitter or full switching, everything we can design. But sometimes what happens, if we want to make what is happening if the waveguides are different. For example, this waveguide having waveguide width W1 and that is having W2, that means beta A not equal to beta B. So, in that case, how to deal mathematically, how it works, how to design, right. So, we need to understand first, we need to develop a coupled differential equation. That is very straightforward. Whatever you have learnt to demonstrate to derive coupled equations in a single waveguides with multiple modes are excited, and when there is a perturbation that can be periodic and so on, we have already developed the coupled equation. Same method we can use when the two modes are belong to two different waveguides. I want to see if they are coupling, then how they are interacting, how power exchange will be there. It is almost identical, but not exactly whatever we have developed for a coupled mode equation for single waveguide. Okay. Let us see how it goes. Individually, waveguide A gives this solution. Individually, waveguide B gives this solution. A is constant, normalization constant, B is normalization constant, A square equal to 1 watt we can consider, B square equal to 1 watt, they can carry individually 1 watt, and normalization constant according to the normalization constant for waveguide A, this is EA star multiplied by EA, that will be 2 omega mu by beta A. Of course, if it is non-magnetic material, you can always consider mu naught, that is fine. So, similar for mode B, when they are not coupled, this is good, uncoupled solutions we can write, right. And in this case, when they are uncoupled, if you try to get this overlap, EA star xy, EB xy, dx dy, okay, in that will be actually, it should be equal to 0, because this mode, if they are uncoupled, that means their overlap, whenever EAXY is there, EBXY will not be there. So, one of them will be 0 if they are coupled. If you change the coordinate to coordinate, right, then you will be seeing when this is present, the other value is nearly 0, and when this is present, this value will be nearly 0. So, when they are uncoupled, in that case you will be getting say 0 value, but if they are coupled, if some area, for example, in this region if you just see two modes are there, EAXY, EBXY, that region if you see this overlap is not equal to 0. In some area field A is also present, field B is also present. So, both are present. Here we can say that field A is absent, here field B is absent, EB is absent, but in this region both are present. So, that means you can get, if you integrate minus x equal to minus infinity to plus infinity, y equal to minus infinity to plus infinity, they will be getting non-zero values. So, then if you get a non-zero value of this type of things, then you can say that these two waveguides are coupled. So, for that what we will do, let us try. When they are uncoupled, we can write their solutions, differential equation. How that is done? Let us define the entire structure, the cross section of the directional coupler, if you are considering. Individual their solutions are there, EXY, EBXY, beta A, beta B, that is known to you. You can solve this one assuming this is actually cut, and again you can solve this one assuming cut, then you can get this. Now, you want to solve the entire structure, entire cross section globally. You want to solve Maxwell's equation for the entire structure. In that case, I can say that the cross sectional refractive index profile can be written like that. What is that? I am just giving n square uxy. N square uxy, that means uncoupled, that means without the waveguide, what is the background refractive index profile? That gives you the NS, ND layer, that means slab layer and then cover. So, this type of refractive index profile wherever is there, that means this rev is not there, this rev is not there. That is actually you are calling as a nu square xy. Okay. So, in this region it will be NC, in this region it will be NC square it will be there. So, that is actually that type of profile, that means the REEP, other than REEP, whatever the profile background, because only REEP gives you the sense that waveguide is present. So, this region actually gives you, this region silicon is there, that means you have a waveguide. This region silicon is there, then you have a second waveguide. So, if these two regions absent, then entire cross section if you map, whatever the refractive index profile you get, that is actually nu square xy. Now, I can consider delta Na square, that means only the additional part, that means this part, the region, this region, what is the additional refractive index? You have Nd square minus Nc square, that is actually your delta Na square, Nd square minus Nc square, only this region, that actually, that presence actually gives you waveguide A. Similarly, this one we can say that Nd square minus Nc square in this region, in this location, in this coordinate system, in this particular region, that will be, that presence of that one gives you the definition of refractive index profile for the waveguide B. So, that is why I said the background and then additional region, whatever the refractive index for waveguide A, that is defined here, that is for, that is indicating waveguide A, and that is actually indicating, mathematically you can represent that, okay, background, and if we consider this one, if I consider this one equal to 0, that means I am considering only waveguide B. If I am considering this one equal to 0, that means I am considering only waveguide A. So, this delta 1 0 means waveguide B only, Nu square, this one waveguide A, and this one 0 means this is waveguide B. So, similarly, that means I can actually form my differential equation for waveguide A. For waveguide A, we know the solution should be A xy e to the power j omega t minus beta A z. That is the waveguide solution, more solution for waveguide A, when delta n b equal to 0. So, delta n b is equal to 0, normal scalar wave equation if we write, del square del x2, del square del y2, omega square by c times n square, omega by c square, n square. That means, you know, this is the omega by c square by n square, that means what is the refractive index, and this side will be the propagation constant. So, that is why I have not put del del z2, that should be equal to minus beta square, beta A square, right. So, that is what right hand side goes, beta A square, that we have used earlier also. For waveguide A, if only this mode is present, waveguide B is not there, absent, then this is the differential equation you need to solve. And when individually, when waveguide A is not there, only waveguide B is there, we have to solve this identical equation for waveguide B. That is when they are uncoupled. As far as they are uncoupled, you can use that one. But I want to see they are coupled and this type of refractive index I define. Then what I need to know? I can define this, they are actually interacting. That means, the solution I considered earlier, that A e a x y e to the power j omega t minus beta a z, that is actually E A equal to, and E B equal to B E B x y e to the power j omega t. If they are non-identical, you can also consider something like this, right, and A square equal to B square, you can consider 1 watt, and A equal to 1, B equal to 1 we can consider, right, normalization constant we can consider. However, when they are interacting each other, you are breaking the orthogonality condition. That means, like coupled mode theory, we consider that they are longitudinally, their amplitudes keep on varying, because they are they are interacting, power can exchange each other. So, you can get longitudinal z direction along with this phase, you have longitudinal amplitude evolutions you are having. Similarly, Bz for waveguide B, amplitude evolution you will see in the forward direction. And we are considering that this, they are coming so close that the perturbation of the second, due to presence of second waveguide, it is not really very high we are considering. It is a weakly coupled we can consider, both the waveguides are weakly coupled. That means, the evanescent tail is almost going to 0, and there you see the presence of the second waveguide. Okay. So, in that case this is the situation. I can say that what is the total field in the system. I can express that okay, total field this one, z dependent variation of the waveguide A, z dependent variation of the waveguide B, their superposition I can consider as the field strength. And corresponding differential equation, if I want to use that as a solution, corresponding differential equation, instead of just waveguide A you are considering this refractive index, waveguide B you are considering this refractive index, we are considering presence of both the waveguide in the wave equation. In the both the waveguide we are considering wave equation, and this is the field, and in that case you have beta A and beta B, their combination is there, along with that is the z dependent phase, but it can happen that this Bz and Az that can also be complex, and that complex value can be adding here. So, beta A and beta B will be modified then. So, z dependent function is something different now. So, I cannot write like beta A square, beta B square like a individual eigenmode solutions like a waveguide A and waveguide B, rather I keep del 2 del z2 here and omega square by c square epsilon r and total field I am considering. That is same as coupled mode equations we have developed, same process, just we are just restricting ourselves that okay, there are two modes and two waveguides, okay, they belong to two different waveguides, that is the difference. So, now slowly varying approximation, if I just use here, right, then I have to same way I have to find out del 2 E by del x2, that means only x dependent function, del 2 y by 2 del 2 same function, del 2 del z2, you have this term you will be getting. So, you can consider that same way dA by dz should be much greater than d2a by dz2. Second order derivative is very small because the amplitude is evolving very slowly. So, if you just go for second derivative, it will be approximately equal to 0. And similarly, dB dz, that is much higher than d2b by dz2. So, you use same way whatever you used for coupled differential equation for a single waveguide having supporting multiple modes, the same way if you do that and you come up with a simple few algebra you can use. Of course, some point you will be getting also this factor also will be appearing whenever you are substituting this one and a little bit you are simplifying, then this type of factor will be there, then all this term will be cancelling each other because some portions you will be getting here, some portion will be like this, and that will be actually you can cancel because this minus this, that will be 0 will be putting, and then ultimately we will be getting one equation like this, left hand side, and right hand side you will be getting like that. So, little bit of algebra I have just skipped, you can do by yourself, just not necessary because only it will take lengthy equations only, but straightforward. You will be getting this two type of equation straightforward. So far so good. So, left hand side you see the evolution term of the field dA by dz in waveguide A. Also it is coupled, another term is there, evolution of the waveguide B, and right hand side you see some kind of perturbation term delta NB square because of the waveguide presence delta NB and waveguide presence delta N square, this terms is there. So, this is something we get. In this type of situation, it is considered slowly varying approximation. In this type of consideration, in coupled mode equation derivation, what we consider, we used one trick, okay, dropping factors j omega t, because every term if you see here, everywhere j omega t, j omega t, j omega t is there. So, you just drop that one, right, that will simplify a bit, and then what you do, multiplying E a star x y e to the power j beta z. So, E a x y e to the power minus j beta a z complex conjugate of this one, you multiply both sides and integrate over waveguide cross section x y entire structure. We get this one first term. So, if you see first term, this one E a star x y means this will be coming like additional E a x y star E a x y and e to the power plus j beta minus j beta a, that will be cancelled, dx dy. That is the first term, and second term E a star E b, E a star E b, that is what you are getting. E a star E b, E a star E b here, and right hand side also E a star you multiplied here, E a star you multiplied here. Just straightforward, you just multiply this one and integrating over waveguide cross section, that is it. So, left hand side, this is equal right hand side. So, this is your left hand side and this is your right hand side. Now, what is there? Here if you see this term and this term, if you compare left hand side, just compare left hand side, only concentrate on left hand side, two terms are there. In these two terms, if you see E a star E a, that means waveguide mode in waveguide A, that is actually, you know, that should be first term will be 2 omega mu by beta, that is known to you if they are normalized. A is initially normalized to 1 watt, right, waveguide A. So, that should be 2 omega mu by beta, mu naught you can put simply. But here this one if you see E a x y, that means profile of waveguide A and profile of waveguide B. So, if you this is non-zero, no doubt about it, but you compare with this, whatever value you will get, that wherever sometimes some majority region you will be getting E a equal to 0, majority region you will be getting, where E b is there E a 0, where E a is there E b will be 0, but here E a star E a star. So, that is why this comparing these two only, we just consider this one E a star E a is much greater than this one. So, we are just ignoring with respect to this one entire structure, we can ignore this one, we can concentrate this one, then we can see how it is evolving only A. I can forget about B, and right hand side I kept as it is, whatever is there I just kept. A z, first term you do not have any exponential term because e to the power minus j beta a and e to the power minus j beta a was there, z is there, and you multiplied e to the power j beta a z. So, they will be cancelling and star will be there, E a star, E a is there and this E a star E b, and obviously you see that now this is slightly different, E a in between delta and b square is there, then you are integrating. So, you cannot just simply use your orthogonality condition 2 omega mu by beta, because in between delta and b square is there, E a star there, but delta and b square is there. So, it is orthogonality condition 2 omega mu by beta, you cannot write. If this was is 1, then fine, you could write. Now, right hand side you see this one. Okay. So, you just simplified it. Now, after removing this one, that ignoring that part and applying the 2 omega mu naught by beta a, left hand side will reduce to first term only. So, that means what you have done? You have just put 2 omega mu naught by beta times this one, and this one you removed, then you are getting this one left hand side. Right hand side I kept as it is, right. Now, left hand side I want to keep this one and this beta a cancel, right, and c square means 1 by c square, you know that is actually nothing but mu 0 epsilon 0. That means, left hand side mu 0, right hand side mu 0 will be cancelled, right. So, and this omega square will cancel 1 omega. So, that means, right hand side will be omega and 2 times 4, beta obviously cancel, minus j will come there in the denominator plus j. So, we can get this thing, left hand side only I have left dA by dz, and right hand side I simplify, then you are getting minus j omega epsilon 0 by 4 this one and omega epsilon 0 by 4 this one, and along with that you have this term also. Now, you know there also in case of coupled mode equation for single waveguide you have defined kappa, right. So, here also we can define a kappa, but there are two different type of kappa is there. You see E a E b in between delta n a square, E a in between delta n b square. That means, it is a scattering of mode A because of the presence of second waveguide. This is what it means. Scattering of waveguide A because of the presence of second waveguide delta n b square, and this is actually scattering of B, something adding to E a because of the presence of B, field B. Okay. So, we define this one as a kappa AA. Why AA? I have just taken this A and this A, and in between, when both are A, in between you have to see the waveguide presence of delta and B, that is what. So, that is how the symbolized, it is symbolized. I define this one kappa AA and this one A and B. When you are writing kappa AB, you have to see refractive index of the waveguide A. When you are considering both are A, then refractive index of the second waveguide you have to consider. Waveguide B, refractive index perturbation of the second waveguide you have to consider, that is what kappa A, and this is kappa B. Then if this can be computed easily once you know the mode field distribution, and then you can easily calculate delta NB square, what is the presence of deep structure there, delta N square, then you can calculate easily. So, once you know this calculation, your equation is very simple now. Omega is frequency. What is that? We can write like this. You see, this is the kappa AA AZ, kappa AB BZ. That means, I have related a coupled equation of related to amplitude of the waveguide A. This obviously this is a function of Z, right, and kappa A is defined like that, kappa AB is defined like that. Obviously, you should know that I know how to calculate using full vectorial method EB, XY, they are known, and also we know that what is the propagation constant for waveguide A, what is the propagation constant of B. Then I have defined that the mode field in waveguide A is like this, mode field in waveguide B is like that, that AZ, BZ I need to solve, then I can actually get every point along the direction what is the field strength, total field strength associated with waveguide A. What is the field strength associated? My intention is to find out AZ and BZ. We have to solve AZ and BZ depending on the kappa A and kappa AB, kappa A and kappa AB, we know that, and because of that presence, because of the perturbation presence, I will be able to predict what is the field. And obviously, if I know that AZ and BZ, their solutions will be complex, they can be complex. Okay. So, according to this equation, you see they can be complex, this is J, that is complex. So, once you know the complex value, the complex relationship, then you can write something AZ, something e to the power j phi 1, and this can be written as Bz e to the power j phi 2. Then I can find out what is the phase difference between them. That is the ultimate goal. Phi 1 minus phi 2 is the phase relationship. So, two waveguide, when I am separating at a particular point, I know what is the amplitude, I will be able to know, and I will be able to know the phase also. That is why coupled mode equation is required. You cannot just simply use your super mode principle, working principle knowledge to find out what would be the phase between the outcoupled waveguide, outgoing waveguide field. So, this is what I have derived, that evolution of amplitude in waveguide A, but it involves what is the field strength in waveguide A as well as what is in the waveguide. I need another equation for Bz. What I will do, instead of multiplying EA star xy e to the power minus j beta Az, this one star, and integrating, what I will be doing, the original differential equations we have got, EB star you multiply and you multiply e to the power j beta Bz. Then you will be getting another set of similar equation, but belongs to that will give you the evolution of the waveguide, that is B evolution. Okay. So, then I can get this type of equation. You see another set of equation you will be getting. Here I will be writing kappa AA, you will be getting kappa BB. Here I will be writing kappa AB, you will be getting kappa BA. So, otherwise same. So, you get kappa BB, similar type of epsilon, kappa ABC, EA delta NB square, EB delta NA square, that is delta NB, and this is delta NA, because BB is there, that is kappa BB, right. So, BB because of the delta NAs, and BA because of the presence of delta NA square. You see that is actually kappa AB, and this is actually kappa BA, B star, A star. So, A and B, they are actually symbols will be interchanged. One mistake is here, this should be because A will become B and this B will become A, this A will become B also. So, if you see derive that one, that will be also B. That was an intentional mistake, so that I can discuss one thing here. Okay. So, this would be delta NB square. Good. Thus, we have two equation, two coupled equation. this can be computed, this can be computed, this can be computed, this can be computed. Now, only thing is that in this equation kappa A known, kappa AB known, kappa BB known, kappa BA known. Normally, we can show that this kappa AB equal to kappa BA star, you can get also. And if it is identical, then you can write also kappa AA star equal to kappa BB star also, identical waveguide also in case. Normal case, this thing always complex conjugate, if you see, they are actually complex conjugate. Almost nearly, if it is identical. Of course, this is, if this is identical, this will be there, because delta n square, delta nb square, here this should be also identical, then only you can see this one. Okay, cool. So, coupled differential equations we have this coupled differential equation, and we just need to solve Az Bz. Once we know solve Az Bz as a function of z, what is the field strength, what is their phase relationship, everything will be known. Okay. Now, we will try to, next lecture I will try to solve Az, Bz, and of course, we will be considering that this waveguide are not identical first, and from there we can just see if that is identical, what is the consequence. If non-identical, what is the consequence. So, accordingly, depending on the consequence, I can design according to our desired specifications, what we need. Okay. I stop here for this lecture. Thank you.